The standard deviation is a measure of variability. It tells us how spread out our data is. In a normal distribution, 68% of our data falls within one standard deviation, 95% falls within two standard deviations, and 99.7% falls within three standard deviations of our mean. Therefore, the bigger our standard deviation, the more spread out our distribution will look. To demonstrate, if we gave a random group of people a survey to gauge their level of fear associated with diving with sharks, we would assume most people would have a healthy level of fear. Some would be pretty comfortable, and others quite afraid. Here we might find that our standard deviation is 10. Now if we administered the survey again, but this time threw in some professional shark divers and some people who have a shark phobia, we are naturally going to have some more extreme scores. This makes the average distance to our mean, our standard deviation, larger. Our data is more spread out, more variable. Likewise, if we were to administer the survey to people who had experienced diving before, we might expect fewer extremities and less variability in our data. So we might find a small SD and our data might look a little something like this. So how do we calculate the standard deviation? It's not as scary as it looks. We start by finding the distance from each score to the mean and adding these up. But when we add them up, they sum to 0. So to get around this, we square each score, giving us all positive numbers, which we then add up or sum. Next, we divide this value by n-1 and then take the square root to adjust for our previous squaring. But hold on, why n-1 and not just n? This comes back to the fact that we are dealing with a sample rather than the population. N alone is used as the denominator when calculating the population standard deviation, and this gives us a perfect value for our population SD. But given that samples have fewer points, they are always less spread than our population. This means that samples do a reasonable job, but consistently underestimate the standard deviation if using the same formula with N. And the whole reason for taking a sample is to try and get an unbiased picture of our population. So if we had data for all 515,000 Tasmanians on their hours spent watching reality TV, we would know our population mean and standard deviation, which in this case we will call 0.4 hours. But if we were to take lots of little samples, for example, the students in one class, your sports team or your family, we would find that by using n in our calculations, we would get lots of underestimated values for the standard deviation. The smaller our sample, the more our standard deviation will be likely to underestimate compared to the population SD. With larger samples, we get closer, but still underestimate. So to overcome this bias, we want to make our standard deviation consistently just a little bit bigger. And the bigger the sample, the lesser the correction. So by using n-1, our correction will always be relative to the size of our sample. And with this adjustment, we are able to bump up the SD to reach a value that, despite sometimes overshooting and sometimes falling below, on average more accurately reflects our population SD.